Yeah. Okay. For those who are new to the class and perhaps new to the college here too, I want to get this one more. The projector's coming up. Remind me of your name, please. Remind me of your name.
Ashley.
Ashley, got it. Thank you. There you are. Okay. Just a little bit of a refresher here, because most of the new people, I think, are new students here to Lawson, probably transient students, perhaps, I guess. So just to let you know, what this thing is right here, that little circle with that, and you see time ticking by, that's the recorder. Everything that I say now is being picked up by my microphone on my computer and going to be recorded in sync with what's projected on the board, okay? And that is a sorry little package called Screencast-O-Matic. It slices and dices, but it's a cheap program. That's what the school goes for. But it's out there. And what I do after class, I upload it to YouTube. And then sometime, probably tomorrow mid-morning, I'll finally get around to putting that in your playlist, okay? Now, your playlist is located on Blackboard. Now, those of you from other schools, are you familiar with Blackboard? Most of you, anyone not? Okay. So Blackboard, when you go to this class in Blackboard, there is the home page for this class. There's a series of tabs over here, and on the instructor side, they're blue. I don't know what color they are on the student side. And they're sort of split into groups. And the first group, something like the second, third, fourth, somewhere in there, there's something that says syllabus, okay? I've got your syllabus out there now. I didn't have it there last Wednesday, but it's out there now. So that's there under syllabus. And it says syllabus and book information or something like that. Now, in this tab right below that, it says instructor information. That's where I'm going to put the locator card. I did not put it there yet because I had to find out what room I was going to be in last night's physics class. The first day I went, they had me in one room, and but they said they were going to find out which room it would go to. It turned out being the same room, but I didn't know that for sure until last night. So I've got it updated now, but I don't have it loaded onto Blackboard. I'll do that. That's not very important. Okay? So that's in this group. In the second group down here, there's one of the tabs that says handouts, PPTs, that's PowerPoints, and more. Okay? And in that group, or in that tab, you'll find, I don't know if this order is correct, the research paper instructions. Yes, okay. And that's one place you'll find it, right there, static form. And then you'll find all of the PowerPoints that we will possibly use this term. Probably a few more than we will use, but I put them all out there, okay? And they're in static form. And then at the end of that, and I, again, can't remember what order, you have to scroll through a lot of them to get down to that. And you must have just added to class, right? Yeah. Okay, so let me fit you in here. I know your name's Ryan, but I can't think of your last name.
Edwards.
Huh? Edwards. Edwards, I knew that. Okay. You still go by Ryan? Okay, no aliases this time? Okay. All right. Okay. Boy, this is getting crowded with all the new people. Good to see that. Okay. So I was just talking about on Blackboard. So under this of handouts, PPTs, and more, the research paper assignment is there in static form. And then all the PowerPoints are there in static form. And I mean, they go on and on and on. Okay, every section in 5 chapters has one, so they're all there. And then and I can't remember the order of this, but one of the ones down here at the bottom will be, I think it's at the bottom, Math 125 YouTube videos. Okay, that's the one for the folks who weren't here last time. You need to go to that. Okay, and that video has everything that we said. We got started a little late because it was first day of class. People were wandering around lost in the hall, and classes were in the wrong place and various things, and I was being called out periodically, so we got started late, but that's where you can find out everything we talked about in class. Okay, we talked about the syllabus, so even though you saw the syllabus up here in static form, here you'll see and hear it in dynamic form. Now, it's not quite the same syllabus because I hadn't updated the one I'm talking about here, but it's pretty much the same. And then I talked about the locator card that you don't get to see up there, but it's there, not for this term, but last summer's, but it's pretty close to the same. I explained the differences. And then you'll see the research paper instructions. You'll hear me talk about them. Same ones you saw up here in static form. Here you hear it in dynamic form. And then we talked about safety. Please review that to know what to do in case of fire, in case of weather emergency, or in case of, hopefully not, active shooter. Okay, so we talked about those. And then we got started in 1.1. And we did all of 1.1, and that's mostly a qualitative section. Okay, now, by the way, back up a moment. This book has in it a chapter P, which is preliminary. If you feel like you're a little rusty on the pre-calculus stuff, that preliminary chapter is pre-calculus, okay? Good review, like 4 sections, really quick review of pre-calculus. And then we got started in 1.1 and finished it, okay? There were a few homework assignments, but they're pretty esoteric. You know, there's not very much calculation in them, so you might want to look at those as well, okay? And now we're ready for 1.2. Any questions before we get going today? Okay. Now, okay. Then, chapter 1 is limits and their properties, and 1.2 is finding limits graphically and numerically. Okay? Personally, I far prefer numerically because that can be done. My graphing sort of stinks and it's not very precise, but you can do it both ways, and the graphical helps you visualize what we're talking about numerically. So our objectives here: establish a limit using a numerical or graphical approach. What I just said. We'll learn different ways that a limit can fail to exist, and we'll study and use a formal definition of limit. Okay? And I'll tell you now, this is not my favorite part of Calculus 1. The limits are necessary to get to where we need to be, and once we get there, we kind of forget about them for a while until we get into the second part, integration. Okay? So, start with an integration to limits, and if you have your books, this is on page 52. Now, about the books, for the people who just got here, if you listen to the video, or you can read the syllabus, there's a huge portion of the syllabus dedicated to an advertisement for Cengage. Okay, it's called Cengage Unlimited. It gives you one way you can deal with getting the book. That's not the only way. That's just one way. And you can rent the book. You can buy the book. The Cengage Unlimited gives you access to the book, and especially if you have other courses using Cengage books, for one price, $119.99, 120 bucks, you can basically have access to all the Cengage books you will be using this summer. Okay, if you have 2 or 3 courses in it, that's really a big savings. However, they're all ebooks, and if you do want a tangible book, for an additional $8, you can get a hard copy, which is loose leaf. You have to get a binder or something to do. I think holes are punched. So you can do it that way. Or you can rent a book or whatever. Okay. For those Lawson students, this book we'll be using for all 3 terms of calculus. So, Cal 1, Cal 2, and Cal 3. For you transient students, more than likely where you're going back to, they may or may not be using the same text. There's so many calculus texts out there, so go for it. Or you can, like I said, rent the book or just buy it outright. Now, there's something that Cengage does, and several other publishers I think do too. They tie their text to a program called WebAssign. WebAssign gives you additional problems for homework or practice and things like that. It has some good features. It has tutorials, it has other things that are very useful, from what I understand. I had a group of 4 baseball players in my intermediate algebra class last term. No, pre-calculus algebra class last term. And because they had so many games that were out of town or times when they couldn't be in class, even though I didn't make a single assignment from it, I put all the things out there they could use, and they used it. When they couldn't be in class, they watched the YouTube videos and practiced on the problems that were in the WebAssign. So I know some students really like them. I don't have it set up yet. I'm going to try to do that soon. But I found out yesterday my boss wants all my evaluations done by the end of this week, which is not going to happen, but I'm going to get working on them. And I have, and if you'll notice on my locator card and syllabus, Mondays and Wednesdays, I have this class from 8:30 until 11:25. I have a big 5-minute break before Cal 2 starts, and that goes from 11:30 to 2:25, and then I have another big 5-minute break before Cal 3 starts at 2:30 until 5:25, and at 5:30 I eat my lunch, okay, because I only got 2 5-minute breaks. I'll probably run down to my office and grab a granola bar or something, but I've not got any time on Mondays and Wednesdays. Tuesdays and Thursdays, that's when the bulk of my office hours are. Now, for you folks, you have the biggest chunk of office hours available to you on Monday and Wednesday because I'm usually here from 8 to 8:30. So if you do have questions, come here a little early and you can catch me on Monday, Wednesday. Otherwise, you basically have to either wait till after 5:30 or see me on Tuesday and Thursday. Tuesday and Thursday, my biggest chunk of office hours are from 10:45 in the morning until 4:30 in the afternoon. I have a differential equation class early and a physics class late. So the rest of the day, those classes didn't make. Linear algebra didn't make. Physical science didn't make. So I have a pretty good series, and that's on Tuesdays and Thursdays. And I'll explain this also. On Fridays, I'm on the Birmingham West Campus, and I have 4 hours of office hours there, 8 to 12. However, we only have this Friday, day after tomorrow, and then for the months of June and July, the college is closed on Fridays. We go to a 10-day work week, 10-hour work day, and we do 4-day work week then. Okay, so I'm not available on Fridays, June and July. Then the first Friday in August, which is at the end of the term, we're back on that Friday schedule again. So this Friday is the only Friday you'll see me over there until the end of the term, if you need to catch me there. There's quickly my office hours. Okay. All right. So let's get back to this. Introduction to limits. I referenced the page numbers. Page 52 in your text. I'm having some trouble seeing because I have a cataract in this eye, my short, close vision eye, and things get pretty fuzzy at times. So it's going to be removed second Thursday, I think, in June. That's when I have it removed. I already had this one done, but that's my distance vision eye, and it's hard. I can't read with it either. Okay. So to sketch the graph of this function, okay, what would you do? Talk about graphing, you finding limits graphically. What would you do to sketch the graph of that function? A little louder. Plug in values. And set up sort of a t-table and go like that. Is that what you're meaning? Excellent way to go. Okay? Now, remember I said, for those who weren't here last time, everything that's projected, my arm waving, you won't see. Okay? That doesn't get picked up by the thing. But I have an ionizing pen, so what we'll do here is set up our, let me get my pen set up. There we go. Okay. All right. I really need to go higher than that, so let me. Okay. Something like that. Not very much better. So give me a point. X equal 2? Okay. So x, alpha of x. Okay. You gave x 2. What would that give you? Huge number. 1, 2. 2 cubed is not a huge number. 2 cubed is 8 minus 1 is 7 over 1. So that would be 7. 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4. Yeah, that one. Okay. That would be at 2. Okay, there's a point. Pretty ugly graph, and this flicks off every now and then. To 2, 7. Give me another point. Another x. 3. That one I know will be off scale. Okay. Here's Devin. Okay. Because 3 cubed is 27 minus 1 is 26. Divided by 2 is 13. Can't get it on the graph. So it's somewhere up there, way up there. Okay. Give me another one. Let's not go any further that way. Second. Negative 2. Okay. At negative 2, it's going to be negative 8 minus 1, right? Negative 9 divided by negative 3, which would be positive 3, right? All right. Jalen? Yes. Yes. Okay. I've got a really good memory. It's just short, so we'll forget names many times. Okay. All right. So I didn't write them down, but you gave me 3, and that was going to be something like 26 over 2, which is 13 and a half, was it? I don't remember, but it's off scale anyway. And then this one was negative 2, and that was positive. In fact, I could have done way down there, couldn't I? That's positive 3. Okay. All right. I don't know why it's so flicky today. All right. Give me another one. Second? 0. Ah, my favorite. What does that give you?
0.
1. All right. Okay. Give me another x. 0, 1. 1. Okay. When we choose 1, what does that give us? Uh-oh. SpaghettiOs, undefined. Okay? You cannot divide by 0. Okay? So at 1 we have undefined. Okay, not quite. Back when you were in algebra, anytime you tried to divide by 0, they'd say undefined, undefined, undefined. Okay? Now that you're in calculus, now that we're talking about limits, and the book doesn't mention this much, but to me it's a far easier way to think of things. If you have a 0 in the denominator, a lot of times that is undefined. But now that we're in calculus, look at the numerator too. What will the numerator be? It'll be 0 also. Now, in any universe, mathematical universe, the dividing by algebra universe, dividing by 0 is undefined. But in calculus, when you have a 0 over 0, that's what we call an indeterminate form. It's not maybe undefined. Some of them will be undefined. But other times, there may be a limit. Okay? So that's the place that we're going to be of interest where x is equal to 1. because that makes your denominator 0. But it also makes your numerator 0, so we don't know what's happening there for sure. Okay? Now, so let's forget about 1 for a minute. Let's give me another x. Well, I guess we hit them, most of them, didn't we? We didn't hit negative 1. What did negative 1 give us? A little louder. Okay, 1. Okay, very good. So negative 1 will give us a 1, because that would be a negative 1 minus 1 is negative 2, and negative 1 minus 1 is negative 2. Negative 2 over negative 2 is so. There must be, we think, probably a minimum somewhere in here. I'm not about to go looking for it. Let's try to see what happens if we do a negative 3. We couldn't do a positive 3. Let's see what happens with a negative 3. Numerator would be negative 28. Denominator would be negative 4, right? So that would be a 7. There we go. We're right there at 7 again. You know, this is looking an awful lot like a parabolic kind of shape, isn't it? Okay? With one problem, though, we don't have a value here. But it seems like it looks like a parabola other than that. Bizarre. Now notice we have a hole in the graph because you can't plug a 1 in there. But otherwise it looks like it's going to be a parabola. Now we could have told that for sure if we had done something else first. Anyone think what we could have done maybe? By the way, use every trick in your arsenal, okay? Fill up your tool belt with all the little tricks and try it. Anyone got an idea what we could have done to that function before we ever got started? Second? How? A little louder. I'm hard of hearing, so I heard someone saying something.
Is x to the third, is that a trinomial?
Okay, no, that's a third degree binomial. Okay. But what about it? Okay. Now, by the way, what kind of function is this? Anyone remember the name from pre-calculus? It's a ratio of two polynomials. What's that called? The first 5 letters of the name is ratio. R-A-T-I-O. Rational function. Now, what's usually the best first step to simplifying a rational function? That's what you said, simplify it, right? They're polynomial functions, numerator and denominator. Factor everything in sight. Perfect. Now, that denominator is not factorable, but is that numerator factorable? Oh, what would it factor as? Oh, do you remember how to do that one? Goodness, that's so jerky today. Come on back. There we go. Say again? Okay, that works with unfoiling works predominantly well with quadratics. It doesn't work with cubics, okay? But this is a difference of two perfect cubes. Oh, we remember that from intermediate algebra, don't we? How do you factor difference of two perfect cubes? The cube root of the first one, x, same sign, minus cube root of the second one, 1. There's the first factor. Now, do you remember the other factor? It's a little strange. Obviously, to get an x cubed here, it better be an x squared here. I don't know why it's doing this, but it'll come back. Right, there it is. Okay? Now, here, say again, remember it?
Like x squared
plus x, okay? Okay? Okay. All right. Okay. Here's what you do. Here's how I do it. My little rule. I've never seen this in a book, but this is what I do. Once you pick out that first factor, forget about this and look at this one. Square the first one, opposite the product of these two. That would be a plus x. And then the last one, square the last one, plus 1. So it would be an x squared plus x plus 1. And guess what happens here? You eliminate, factor out the x minus 1s. And that gives you the parabola. And that is the parabola for this one. And let me just give you a hint now. You'll never be able to factor this any further, okay? If you had done difference of two perfect cubes and pull out the first one, the binomial factor, the trinomial factor will never be factored, okay? But this will be the graph of it. Except that, even though you eliminated it here, it wasn't eliminated in the original problem. You have a hole in the graph at x equals 1, okay? So that's why it's a parabola, because that you're left with a quadratic, and that's the graph of a quadratic. Now I didn't fill in all the table there; it's easier to just plot it. Does that make sense? Okay. So that's a trick. Hang on to the trick. Okay. What they do, and it's basically somewhat the same thing we did. I'm going to erase what we did. What they do is to get an idea of the behavior of the graph near 1, x equals 1, because that's the problem place. That denominator had a x minus 1, so you can't have x equal 1. But see what happens. It says use two sets of x values, one set that approaches 1 from the left, and one that approaches from the right. Okay? So they're getting close to 1. So they started out here at 0.75, and that gave you a value. They got 0.9, that gave you a bigger value. 0.99 gave you a bigger value. 0.999 gave you a bigger value. 1, plug it in your calculator, you get undefined. Bad domain, something like that. Go from the right-hand side, 1.25, that gives you a value. 1.1, a little bit less. 1.01, less. 1.001, a little bit less. Both of these, as you're getting closer and closer to 1 here, which you can't be 1, but you're getting closer and closer to 3 there. And that's why, whoops. Well, I erased it. Sorry. But this is their graph. As you approach this, it's getting greater as you're going close to 1 from the left, lesser as you approach 1 from the right. Both of them seem to be approaching 3. The limit is 3. The value is not 3, but the limit of that is 3. And you can get as close as you want to. 2.99999999999. You know, you'll get closer and closer to 3, but never get there. Or 3.000000001. You get closer and closer to 3, never get there. It's only exactly at x equals 1, you have no value. Okay, hole in the graph. So the graph of f is a parabola. Let's see, did I get everything here? Yeah, I guess we did. Okay. So the graph is a parabola. It has a hole at the point 1, 3, shown here. Although x cannot equal 1, you can move arbitrarily close to 1. As close as you want to get, and then the result of f of x is moving arbitrarily close to 3. It's not arbitrary, you're moving closer and closer to 3, but you'll never reach it. So using limit notation, and I don't know if you've had it before, here's what it looks like. LIM stands for the limit of f of x, which is that function right there. As x approaches 1, it can't equal 1, but as x approaches 1, the limit is 3. Coming from the left, coming from the right, they're both approaching 3. So that's read the limit of f of x as x approaches 3. That's what this means. It's covered by the time clock here. X, that's an arrow there, approaching 1, is 3. That's the limit. All right. So, indeterminate forms may have a limit. still don't have a value, but they may have a limit. So dividing by 0 is not now a death sentence if the numerator is also approaching 0. Okay? But it may be. You can't always tell just by looking. Some of them may be undefined. 7 divided by 0 is still going to be undefined. Anything other than 0 divided by 0 is still going to be undefined. 0 divided by 0, indeterminate. You can't tell just looking at it. You have to analyze it. This discussion leads to an informal definition of a limit. Later we'll get to a formal one. We'll put on as touches for that. Okay? If f of x becomes arbitrarily close to a single number L, that's the function getting closer and closer to L, our example it was 3, as x approaches some number c from either side, then the limit of f of x as x approaches c is L. Okay? Exactly what we just said. The limit as x approaches c of f of x. If that, the closer and closer you get to c, closer this gets to being L, then that's the limit. Okay. Now, of course, if it is exactly equal to that, it's also the limit of that. Okay? But if it's not, in other words, you can't do it, if it still is approaching that, then that is the limit. Everybody got it? Okay. Here's example 1, top of page 53 if you have a book. Okay? Evaluate this function, f of x is equal to x divided by the square root of x squared plus 1 minus 1. Quantity. At several values near 0 and use the results to establish the limit. Okay? So they want us to do that graphing approach now. Can I jump a little bit ahead and tell you, okay, what we did before, we picked values and stuff and plugged in. We saw it was getting closer and closer to 3. Okay? The graph looked like a parabola, only with a hole there. This is going to be a lot more complicated looking. And what would be the values that would give you problems here? -1 will not be a problem here because that would give you a 0 here, and that would be a -1 over -1, that's going to be 1. So that's okay. There are two places where you have problems. One is where the denominator is equal to 0, then you can't have a value there, or where what's inside the radical is negative. So you're awfully close, you've got to 0, but if this was a -2, you've got problems. In fact, anything less than -1 is going to be undefined. So that's going to be the problem here. We're not going to be able to do a thing with that. Okay? Can't handle that one. But where would this equal 0? That denominator equals 0. What value for x? Oh wait, yeah, x equals 0, then this would be a 1. Square root of 1 is 1, minus 1 is 0, but your numerator is also 0. Okay? So that's another one of those indeterminate points. So yeah, that's where the problem's going to be. Now we have to figure out how to do it. Now, what they're wanting us to do is get closer, values closer and closer to 0. From the left, like -0.1, -0.01, -0.001, you go closer and see what those values are. It's a lot of work, isn't it? And then from the right, 0.1, 0.01, 0.001, see what if it's coming to a value. Can I show you the trick, tool to put in your tool belt, of how to do something like this? Okay? Has anyone ever heard the word conjugate before? Okay? Remember what that was? What was a conjugate? You had A plus B. What's its conjugate? A minus B. Okay? Well, here in the denominator where your problem exists, you have A minus B. So what would its conjugate be? What was its conjugate be? A plus B, which would be the square root of x plus 1 plus 1. Where this is your A, there's your B. Okay? Now, if you multiply by that, in the denominator, you got to do it in the numerator as well, right? You got to be democratic about it. Can't do favor one to the other. So multiply this by x plus 1, square root of x plus 1 plus 1. Because now, what if you multiply by here? What is that over that? 1. When can you multiply by 1? Anytime you want to. It doesn't change the value at all, right? So that's what makes it legal in most states. Okay. Now, what do you get when you multiply a number or an expression by its conjugate? A minus b times a plus b gives you what? A minus b times a plus b. Another intermediate calculus question.
It's a squared minus b squared.
A squared minus b squared. So you have this squared, minus that squared. That's not going to be too bad. What would that be? What is the square root of x plus 1 squared? X plus 1, and 1 times 1 is, and that'll be a minus 1, right? Minus 1 times plus 1 is minus 1. Well, these two go to 0, and you're left with just an x in the denominator, and in the numerator you have an x times the square root of x plus 1 plus 1. But this x, and divide that x away, there you got rid of your problem child, the 0 in the denominator, and what you're left with is here. And as this approaches 0, x approaches 0, what does this approach? X is approaching 0, what does this approach? Plug it in, plug it in. Help me somebody, I'm dying up here. 1 plus 1 is 2. All right. Didn't know you'd be doing such high-level math today, did you? 1 plus 1 is 2. So the limit of this is 2. Okay? Now, can't do anything with those x's less than negative 1. Okay? That just throws the whole thing out. But at x equals 0, we have a limit. Not a value, but a limit. The limit of that is 2. Okay? Now, to me, that's easier than plugging in all those values. 0.1, 0.11, 0.001, 0.0001, you know, all those go from the left, from the right, like this. So, let's do it their way, though, and see what they get. So, they start with negative 0.01, then negative 0.001, then negative 0.0001. This was 1.99499. 1.9950, 1.9995. You know, where's that heading? Getting closer to 2. From this side, 0.01, 2.004999, okay, and 0.001, 2.00050, 0.0001, 2.00005. What's that getting closer and closer to? 2. Approaches 2 from the left, approaches 2 from the right. Stand up, sit down, fight, fight, fight. We have our limit. Okay. The limit of f of x is 2. We did it algebraically. They did it numerically. Works both ways. You can estimate the limit to be 2. Now, what is this function going to look like? I think they're going to graph it next. Yeah, here it is. Anytime you have a square root function, especially thinking of the one we wound up with before, you know, after we did the limits, can't be any value left of minus 1. It can be minus 1. At minus 1, this would be minus 1 over minus 1 is 1. We said that before. That's where it stops here. You can't go any further to the left, and then it acts like a square root function from there on. Okay? With the exception x equals 0, you have a hole in the graph, and y is equal to 2. So x equals 0 is undefined, or indeterminate. You still don't have a value there because you can't divide by 0. And that gives you a 0 when you put x equals 0 in here. So you have a hole in the graph there, but other than that, it looks like a square root function. Make sense? All right. So those two have limits, even though you have a 0 in the denominator at a certain value. but because you have a 0 in the numerator, it's indeterminate. Both of those wound up having limits. Does that make sense? See what we mean by limits, okay? Don't have a value there, but as you get closer and closer to 0, you get closer and closer to 2, from the left and from the right. All right. They're skipping example 2. So let's go back and find some white space. I think this will be our best bet here to work example 2. All right. Find the limit of f of x as x approaches 2, where f of x is equal to, now this is a piecewise defined function, is equal to 1 when x is not equal to 2, and it's equal to 0 when x does equal 2. Now, before I favored algebraic techniques. This one, graphing is about the only way to go. So we need to really graph this one, okay? So I'm going to put my axis here and here. I have 1, 2, 3, 4, 5, 6, negative 1, 2, 3, 4, 5, 6. Okay, they're not evenly spaced. 1, 2, 3, and negative 1, 2. Okay, got there. Now, give me an x. 4. Okay, got it? And what's the value of f when x is equal to 4? Second? You may have said it, I can't hear. 1, perfect. Okay, give me another x. Any old x. As long as it's on the board here, don't give me minus 543, that's not on the board. Give me another x. Any x. Second, 0. When x equals 0, what's your y value, your f value? 1. Okay. Give me another x. Second. Did someone say something? 2. What's your value of f there? 0. Okay, got it. Give me another x. It's not that hard, folks. 3. And what's your value? 1. Give me another x. Negative 2. What would be your value? 1. Okay. Are you seeing a picture of emerge here? Okay. Every place for every x, any x you do, the value is 1. Except for x equal 2, and then it drops down to 0. And then anything from there on, it goes back to being 1 again. It's a constant function of 1. So it's a horizontal line, should be horizontal anyway. Except at this point right here, your x value is 0. So you don't have this one now. Okay. Now, what's the limit of that as x approaches 2? Either from the left or the right. 1, exactly. It's 1 when you come from the left. It's 1 when you come from the right. So the limit is 1 at 2, but the value is 0 at 2. Okay. So this is a situation, the limit exists there, and it's different from the actual function value. This one does have a value at x equal 2. It's 0, but it's not its limit. Okay, so that's sort of an interesting illustration, and we'll get back to that later. Okay? Now, we've been doing numerical approaches. That's what the book did. Graphical approaches here, and we've done that too. The other approach is analytic, and that's what I cheated and told you about. Okay? But we'll get back to that in a bit. Let's go on to, any questions on that before we leave it? Is it making sense? Okay. Now, limits that fail to exist. Don't worry, there are limits that fail to exist. Okay? It says show that the limit of the absolute value of x divided by x does not exist. Now, sort of a shame they told you what the answer was. They just said, show it to you. How would you go about doing that? Anybody? What's sort of problematic with that expression there? It's what? Yeah, there's a limit. Yeah, that's always problematic, isn't it? No, what's the absolute value? How do we define an absolute value? Does anyone know the formal definition?
Something that can't be negative.
Okay. So basically it's a piecewise defined function. That's where, see, this is not a rational expression because that numerator is not a polynomial. The denominator is a polynomial, but the numerator is not. So here's what you would do. It's sort of like that last one we did that was piecewise defined. This would be the absolute value of x divided by x would be defined as x over x anytime x is greater than or equal to 0, and it would be minus x over x anytime x is less than or equal to 0. Now why is that? Because the absolute value of a positive number is its own value. But the absolute value of a negative number is the opposite of it. So that would be, and I shouldn't have put the equal sign here. They usually leave one of them off, and that's usually the one they leave off. Okay? So this is a piecewise defined function. Right? Does that make sense? Okay? Because the absolute value is x when it's greater than or equal to 0, negative x when it's less than 0. So you put that over x, and there's your piecewise defined function. Okay? And what's obviously the problem issue? X equal 0, because you can't divide by 0. And both of these are indeterminate forms. 0 over 0 and 0 over 0, right? So, does that guarantee you've got an answer? No. It's indeterminate. Okay. Well, what is the value of that numerator for any value that's greater than 0? X over x is 1. Okay, so that would equal 1. And what is it when x is less than 0? Negative 1. Okay? And guess what? If you were to graph that, it would be 1 up here with a hole there, and negative 1 down here with a hole there. Do you think you're ever going to get a limit? No. This is approaching from the left, it's approaching negative 1. From the right, it's approaching positive 1. No place can you ever get those to equal each other, ever. So this is where a limit does not exist, where the limit from the left is different from the limit from the right. Okay? So that's one illustration of that. Okay? Let's erase that and watch how they did it. Consider the graph of the function that, okay, yep, that's the one that we have inside the limit. Do the graph of it. And this one, again, graph is the way to go. Because the absolute value of x is a piecewise defined function, it's x when x is greater than or equal to 0, minus x anytime x is less than 0, because, as Patrick said, it always has to be positive, can't ever be negative. It can be 0. In fact, it's 0 at both of these, where those are 0. Okay? So because of that, then you take this and divide it by x, you get 1 for any positive values. Negative x divided by x gives you negative 1 for any negative value, so this is almost as pretty as my graph. It's approaching negative 1 from the left, positive 1 from the right, can't be defined at either place because you can't ever divide by 0, but guess what? There is no. Now, they have introduced something else here, which we're going to run into later. We're going to introduce this concept of a delta. That's a lowercase delta. And the delta you're going to let get closer and closer and closer to 0. And if, as that delta got closer and closer to 0, the f values of here and here got closer and closer to some value, then you would have a limit. These don't. No matter how small you get your delta, this is still -1, that's still +1. So no way you'll ever get a delta small enough, as long as delta is greater than 0, that you'll ever get those approaching the same number. They will always be -1 and +1. So hang on to that concept of your delta. We'll get there later. Okay? They don't even mention it on the slide here. They throw it up there in the book. But as x gets closer and closer to 0, in other words, delta getting closer and closer to 0, the limit is still +1 and -1. Okay. So that limit does not exist. Okay, yeah, that's what we said before. Absolute value of x over x, dividing this thing by x, gives you a +1 for x greater than 0 and -1 for x less than 0. You can't put an equal 0, and that's something I did wrong. I should never put an equal 0 because you can't have x equals 0. So you lose the equal sign when you divide by 0. Okay, divide by x. So here's example 3. Oh, no, this is continuous. So no matter how close you get to 0, x gets to 0, there will be both of the positive and negative x values that yield x equal 1 and f of x equal 1 and f of x equal -1. Specifically, if delta, the lowercase here as they get to it, is a positive number, then for x values satisfying the inequality, that 0 is less than or equal to absolute value of x is less than or equal to delta. In other words, this is what x is approaching. And delta, you get closer and closer and closer to 0. Okay, you can classify the values of absolute value of x over x as -1 for negative value and +1 for negative value. So any negative, remember delta is a positive number. No matter how small you get, that still is going to -1. And no matter how small you let that delta get, that one's going to +1. So no, the limit will never exist. Ever. Okay, because the absolute value of x over x approaches a different number from the left, right, as it does from the left, then the limit does not exist. Now, they're skipping examples 4 and 5, okay? And we need to do those. So let's go back and do example 4. Discuss the existence of the limit as x approaches 0 of 1 over x squared. What you guess? What would be your first response? What's wrong with it? Where is your problem child? And it's pretty obvious. X equals 0. Because that would be your divided by 0, and that's what we're investigating. What's happening as x is approaching 0. Now, they haven't gotten to the point yet, but this is where I get to go on and introduce you to it. When in doubt, do like the lady, plug it in. Okay? So plug in a 0 here, and what do you get? Undefined. Now is this, indeterminate or undefined? This is undefined. If that was 0 or 0, indeterminate. 1 over 0, undefined. Okay? So guess what? Anytime it's undefined, the limit's not going to exist. It will never exist. Because if you let x get closer and closer to 0, that's 1 over a very small number squared. And 1 over a very small number squared is an enormous number. Okay? And you do it from the left, that's positive and enormous. From the right, it's positive and enormous. Never, they ain't gonna ever touch. Okay? They just keep getting bigger and bigger and bigger, they'll get closer and closer together, but never have a limit. Never have a limit. Because this is an undefined form. So don't even mess around with undefined form. As soon as you see it, say undefined. Or it does not, the limit does not exist. Always. If that was a 0 over 0, you have to investigate. When it's 1 over 0 or 17 over 0 or negative 0.3 over 0, it's never going to exist. Only indeterminate forms are 0 over 0. Okay, so that one really wasn't too bad. The picture of the graph is in the book. I'll let you look at that. Now this next one, these calculus books love them. And, okay, so this is DNE, right? Does not exist. Now, I've had students write that before, but they're sloppy on the D. And I thought, how can they get a limit of 1? No, this is DNE. Okay, never mind. All right. So the next one is the one calculus books always love. Now, here's a place, and for those who weren't here last time, I think I mentioned this before. I've taught from several calculus books. I had a calculus book when I was in college. It was tough, but it was a really good book. They have a revision of that still out, and I have a guy in my Cal 2 class who's probably close to my age or maybe even older, and he had that same book that I did, and he hates these books compared to that. And there were some advantages of that kind of book. But basically, if you look at any calculus book in the table of contents, the chapter numbers are almost identical. Chapter names are almost identical. They may be numbered differently, but the names are almost always. You start with limits, then you do differentiation, then you apply differentiation. So the books are very, very close. Okay? What this book has that most books don't are 3 things, and it's on the back of the cover if you do happen to get the book. The first of these is internet resources at larsoncalculus.com. And guess what? You don't need WebAssign, you don't need any special code package or anything. Anyone can go to larsoncalculus.com. Your grandmother could go to it. You know, anyone. They don't have to own the book. They don't have to be in a calculus course. Who would want to go to it, I'm not sure. But that's one thing, larsoncalculus.com. It has interactive examples, videos, 3-dimensional graphs, videos with Bruce Edwards, who's the co-author of this, editable spreadsheets. Okay, y'all are hungry, huh? You missed breakfast. Okay, never mind. All right, so that's one thing. Well, that's what I was saying on example 5 here. This is one, and it says, see larsoncalculus.com for an interactive version of this type of example. Something, I haven't found another calculus text that has that. Now, the next 2 things are also in the back here. One over is calcchat.com. Okay? Now, that, when I give you your homework exercises, you'll see that at the top of every exercise page, and it's offers students solutions to the odd number exercises in the text. So I will assign to you any of the odd number exercises in each group, and if I would say do those, try them on your own, do them, check the back of the book, because the answers for odds are in the back of the book. If you don't get this right answer, see if you can figure out what you did wrong. If you can't figure it out, don't get frustrated. Go to calcchat.com, and they'll show you how it works. Don't go here first. Do it yourself first. Check the answer. Try to get that answer. If you do, that's yours. Okay? If you can't, then go to calcchat.com, see where you made your mistake. Okay? Now, also in some of the homework exercises, there will be exercises that have a red number rather than a red 7 rather than a black 7. You know, all the others are 1, 3, 5, 6. All of them are black. Everything's black except one will be red. And that's calcview.com. These present video solutions to the selected exercises, and you can watch calculus instructors progress step by step through the solutions. So it's even more detailed. It's a video rather than just the answer. Yeah. So 3 things that most books don't have, and this example 5 is one of those at larsoncalculus.com. All right. And here's what example 5 is. Discuss the existence of the limit as x approaches 0 of sine of 1 over x. Okay? Well, frankly, even though this seems like a really complicated thing, all you have to do is look at here, and what form is that? Undefined. 1 over 0. Plug it in, Remember, Glade? Okay? Plug it in. 1 over 0, undefined. What happens if 1, as x approaches 0, of 1 over 0? Well, if x is negative, that's going to an extraordinarily large negative number and keeps getting more and more negative. When x approaches 0 from the right-hand side, it's going to an incredibly large positive number. So if you're approaching x this way, the sign of a number that is getting bigger and bigger and bigger and bigger, sign just goes up and down, 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 and it just does that forever. It never gets to 0. It just goes up and down, getting closer and closer to 0. Okay? From the right-hand side, it's just doing it in the opposite direction, coming like this, up and down, and it's never going to have a limit. Ever. But you can tell that by looking at this. Don't even mess with the sign. That has no limit, so how could the sign have a limit? It doesn't. Okay? So this is another case where the limit does not exist. Right? To me, all you do is find that you have a undefined form. It's not going to exist. No matter what else you do to it, it's still not going to exist. Okay. Now, if you had just thought I'd be smart and plug a few values in here, you might just get that it's alternating between +1, -1, like the book shows. It's doing worse than that. It's just going forever like this and forever like this, and never going to have a limit. All right. So we've hit 3 situations where the limit doesn't exist. Common types of behavior associated with non-existence of the limit. The f of x approaches a different number from the right side of C than it does from the left side of C. If that's the case, the limit doesn't exist at C. It exists down here, it exists over here, but it doesn't exist at C. Okay? Second case, f either increases or decreases without bound as x approaches C. That's the case of an indeterminate, of an undefined form. Okay, if it increases or decreases without bound, it's never going to have a limit, because without bound, it has no place it's going to. It just keeps getting bigger or smaller. Okay? And the third case, like that last one we saw, f of x oscillates between two fixed values and just keeps oscillating as x approaches C from either side or one side, or it doesn't matter. It can't possibly have a limit. Okay? So those are the 3 situations. Make sense? All right. Now, they throw another little one in here, which I see no reason to do here, but they do it. And this is Dirichlet's formula. Now, I'm not sure if I'm even pronouncing that right. Let me see. I'll put it here. I'll spell it for you for those who don't have a book yet. D-I-R-I-C-H-L-E-T. Yeah. And they even have the guy's picture here. Okay? Here's his function. I guess he had to have a function. He wanted to have one so people will remember him. Okay, and here it is. F of x is equal to piecewise defined function 0 if x is rational and 1 if it's irrational. Now, the domain of that function would be all real numbers, and they would oscillate from being 0 and 1, 0 and 1, 0 and 1, 0 and 1. So no value in the world you pick there is ever going to have a limit, because you can get a rational number close to that or an irrational number close to it, but they're always going to be apart. Now, what use is a function like this? I have no idea. In my mind, Derek Klatt had too much time on his hand. I mean, what is he going to use this for? I don't know. But if you think back that you do have a research paper going, maybe you can find out why he came up with a formula like that. If you want to use him or the Derek Klatt fortune, I don't even know if I'm pronouncing a function, as your paper topic, there's a good one, okay? I don't know if you'll find it very useful, but if you think you would, that could be a paper topic. Okay. Any questions on that? Now, there's one other thing, and this is pretty good, so I will mention it. They don't show it in the slide set. But remember the oscillating function that I had? I probably already erased it, or have I? No, yeah, this one right here. This one right here. If you said, oh, I know what I'll do. I'll plug it into my graphing calculator and see what I get. Okay? Here is what you get. Okay? It actually looks like, in this case, that it has a limit of x equals 0, of y is the limit of 0 as x approaches 0 from the left to right. Okay? It doesn't. Because your graphing calculator only deals with finite little values. And if your finite little value doesn't include 0, if it included 0, it's going to say can't do it. But if it has somehow misses 0, then it's going to give you a graph, and it'll look like it has a limit. So you can't trust. And what they call this is a technology pitfall, okay? Because just because your graphing program doesn't show that it goes, it doesn't explode and go out of range, it just doesn't have a limit there, okay? And unless your graphing package can pick up on that, it's going to look like it has a limit. It doesn't, okay? I promise you it doesn't, okay? So now we're ready for the formal definition of a limit, okay? We're going to put on our tuxes here and talk about the formal definition of a limit. And I reminded you before of that little delta. Here the delta comes into play. Take another look at the informal definition of limit. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x approaches as x approaches, the limit of f of x as x approaches c is L. That's what we call it, okay? Now, sounds fairly technical, you know, look at it. Here's what you watch for. What does arbitrarily close to mean, okay? You got to get a little bit more better definition of that, okay? It's informal because the exact meanings have not been given to two phrases, becomes arbitrarily close to. Here it says arbitrarily close here. I thought it said it in another place. I think earlier it did, okay? So what do we mean by that, okay? And here's the second one. As x approaches c. Well, how close does it approach c? You know, that's, again, not quite defined. So here's your formal definition. Okay, the first person to assign mathematically rigorous meanings to those two phrases was Augustine. I'm not sure I'm going to pronounce this right either. Louis Cauchy, or Cauchy. I don't know how you pronounce that. And his epsilon delta definition is the standard still used today. Thank you so much, Couchy. Okay. As far as I know, he was French. I don't think they have a little blurb on him, but there's another potential paper topic. Who he was, what he did, how did he come up with this, and then basically lots of places how we use it, we still use it. So here's the figure that's going to help us hopefully see this. And here's how it starts, the formal definition. Let epsilon, which is the lowercase Greek letter epsilon, that's equivalent to our E, let epsilon be a positive number, okay? A small positive number. Then the phrase f of x becomes arbitrarily close to c means that f of x lies somewhere in between L minus epsilon or L plus epsilon, because you've let epsilon be a very small number, and L minus epsilon is going to be a little on the bottom side of that, L plus epsilon a little on the positive side of that, upper side. So this would be your L minus epsilon here, L plus epsilon there. Okay? So we usually start at let epsilon be greater than 0. I know this because this is how my calculus instructor back how many decades ago always said. That's how I always start. Let epsilon be greater than 0, and then blah, 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 blah. Okay? So that's where we are. Epsilon is some small positive value. Okay? Now, remember our delta? Delta was a small positive value on either side of your C. So epsilon's on either side of the limit. Epsilon's on either side of your what x is approaching. So that's how the second phrase, as x approaches C, as this delta gets smaller and smaller and smaller. Okay? So, the epsilon delta definition, this is what we're getting toward. So let's get to it. Using absolute values, you can write this as, okay, what we're talking about here, that the limit is somewhere in between these two. So if you do absolute value of f of x minus L, that's the actual value of your function minus the limit as it's going there, the absolute value of this is less than epsilon. Okay? That means f of x is getting arbitrarily close to, or L is getting arbitrarily close to the function. So similarly, the phrase as x approaches C, there's your delta comes in there. It means that there exists a positive number delta such that x lies on either side of the interval, x minus delta to C or xc to x plus delta. Because delta is always positive, so it's one way or another. This fact can be concisely expressed as 0 is less than or equal to x, the absolute value of x minus C is less than delta. Basically what you did was subtract C from all three sides of an inequality here. Subtract C from this, you get minus delta, and you get a 0 there, and you get plus delta here. So basically, the 0, you can put a minus delta less than 0 less than delta, and there's your x minus c there. Okay. So that's the concise, precise definition of x getting arbitrarily close to c. Okay, that is within delta of c. So the first inequality says that the absolute value, because absolute value is always positive, it's got to be greater than 0 then. So that's pretty obvious. And the other says that this, though, is going to be less than that delta. Whatever delta you chose, you can get this as close, to be less than that. So that means you're within the distance of delta from C. They really string this out obnoxiously, okay? So here's the formal definition of a limit. The f be a function defined on an open interval containing C, except possibly at C itself, okay? So x is defined everywhere on this open interval. C is somewhere in that interval. Can't be at the ends because it's an open interval. It's somewhere in there. And x is defined everywhere in that interval except possibly at c. It doesn't have to be defined at c. Okay? The function f. Okay? Let L be some real number. Okay? Then the statement, the limit as x approaches c of f of x is equal to L. The limit of f of x is L when x is approaching c. That means for any epsilon greater than 0, any tiny, you can pick that epsilon as small as you choose. Any epsilon greater than 0, you can then find the delta also greater than 0. It can be very small, such that for any time that the x minus c, the difference between x and c is less than delta, absolute value is less than delta, greater than 0 because of absolute value, then the absolute value of the difference here is going to be less than epsilon. So no matter how small you choose the epsilon, you can find the delta that works. Because you pick this and you look for that. So that's the basic premise here. And that's the formal definition. This means arbitrarily close, okay, and this means as x approaches c. You got a formal definition here. So here's example 6, and these, the simple ones are really easy. And when you get more complicated, then it really gets bogged down quickly. But here's this, okay? They tell you the limit as x approaches 3 of 2x minus 5 is equal to 1. And how could you tell that was true? What you glade? Plug it in. So plug in the 3 here, and what do you get? 2 times 3 is 6 minus 1 is 5. 6 minus 5 is 1. Yeah, we know that limit exists. It's exactly that, okay? So it says down here, find the delta such that, okay, this 2x minus, there's your f of x, or x minus 5, minus 1, there's your limit, f of x minus this, is greater than 0.01. That's your epsilon, okay? F of x minus L, the absolute value has got to be less than epsilon. So you're choosing epsilon of 0.01. Now, if you can't find a delta that guarantees that's always going to work, then the limit doesn't exist. But if you can find a delta, no matter how small you pick your epsilon, then the limit does exist. Okay? So this exists whenever you pick a delta that's less than that. So there's your x minus c is going to be between 0 and delta. Okay. Now, like I said, this one is incredibly easy, just like it was easy just to plug it in. Okay, so what you do here is take this complicated looking thing here, which is what you're trying to prove, and let's see if we can get it to look like that. Okay? Well, the first thing I would do absolute value of 2x minus 5 minus 1, right? That's less than 0.01. It'll come back. Okay? Now let's do the math. Absolute value of 2x, help me, minus 6 is less than 0.01. Right? We're trying to get it look like this, so what could we do here? Factor out a 2, and 2 is a positive number. You can factor it out, and your thing is still going to be, so I'll do 2 times, and what do you have left? X minus 3 is less than 0.01. Well, to get this to look like that, all we have to do is divide by 2. Okay? So then you have, and you know this is positive, so 0 is less than absolute value of x minus 3, which is less than, and 0.01 divided by 2 is 0.005. There's your delta. If you can find a delta that guarantees this works, no matter how small you choose your epsilon, then you got it. Well, whatever your epsilon is, divide it by 2, there's your delta. And that's going to guarantee this works. Okay? So, it said, find the delta, we did. There's the delta. If you pick that delta, you guarantee you're going to get within 0.01, which is your epsilon of that difference between your limit and the. So you choose a smaller epsilon, just divide it by 2, and you got your delta. Okay? No matter how small you choose your epsilon, you can always find the delta that'll work. That means the limit exists. Okay? Now that was incredibly easy because it worked out so nicely. Okay. I'm going to erase my scratch here. Everybody got it? Okay. In this problem, you're working with a given value of epsilon, namely, epsilon is equal to 0.01. Okay? To approximate the delta, to find an appropriate delta, try to establish a connection between the absolute values. Between this one, which is your epsilon absolute value, and that one, which is your delta absolute value. Well, that's pretty easy to do in this case. You just do the math. Remove the parentheses inside the absolute value bars, and that gives you absolute value of 2x minus 6 is that. Factor out the 2, since it's positive, you can do that. And that then gives you this thing is exactly this, and that has to be less than that. So all you have to do is divide this by 2, and that gives you your delta of 0.005. Now that was so obvious that you could just plug it in and see, and then it's obvious when you use this formal definition, and it's easily done. It's when it's not quite so obvious, then the formal definition can get a little hairier, at least, to say the least. Okay. That was, by the way, example 6. Okay? And here's the picture that sort of illustrates, okay, this choice works because 0 is less than that, blah, blah, blah. And then you plug it back in and you get this. It just seems like it's going in circles here, and it really seems that way too. Okay, so you can see from this figure, if you choose an epsilon of 0.01, that means you want this to be within 0.01 of that. Okay, you know your limit is that, so it's between 0.99 and 1.01. To guarantee you're going to be in that, then choose your epsilon. So remember, if x is approaching 3, choose your epsilon within 0.05 of that, and that guarantees on this slope, because it has a slope of 2. If you have this, you know, half the distance, you guarantee you'll be within that epsilon. So from 2.995 to 3 minus 0.005 to 3 plus 0.005 there. You guarantee any value here is going to get you within that. That's your formal definition on a very easy example. Okay. And of course, then, they end it there without doing the difficult examples. Okay? I think, yeah. So let's do second. The break. I love the idea. Okay. So let's stop right there, and we will come back. If I can get my line to draw here. There we go. Okay. We'll make a pause here. All right. Picking up where we left off, we're at the top of page 58. Example 7 was left off here. And again, this is a pretty easy one, so I apologize for making a disparaging remark. They didn't do that. Let's do this one. The limit as x approaches 2 of 3x minus 2, they say, is 4. And this is the thing that sort of gripes me here. If you know what the limit is, well, I mean, there is a reason for it. it just seems almost redundant to be going through these exercises, because really where you really need this is when you don't know what the limit is. But I guess we're doing these with ones you know, so you can see how it works, so then when you get one you don't know, you'll know how to proceed there. So let's do this one. First, does anyone want to dispute that is the limit? How can you check to tell? Plug it in, and what do you get? 6 minus 2 is 4. Yeah, we know that limit exists. So even if they hadn't told us, it would be easy to get. So what would be our approach? Let's see, do they say anything else? No, this time they don't give you an epsilon. You're just going to use the values. So how you prove that's true, you let epsilon be greater than 0. Dr. Osborne, that's how he always started. I had no idea what he was talking about, but I knew you let epsilon be greater than 0, okay? He just said it over and over. So then there is a delta. My writing stinks, by the way. Also greater than 0, such that, I'm going to put double dot there for such that, for any 0 less than absolute value of 2 minus delta, no, x minus 2, I'm sorry, I'm getting everything crossed up here. X minus 2 less than delta, you'll get the epsilon such that the absolute value of 3x minus 2 minus 4 is less than epsilon, not delta, epsilon. I sort of said these backwards, but okay. All right. Well, let's start with the one we know that we're wanting to get toward, the complicated one. See if we can work back to the simpler one. Right? Okay. So, what would you do? Pretty similar to what we did before. What would you do? Anybody? A little louder? So, what do you say again? Okay, remove parentheses, 3x minus 2 minus 4 less than epsilon. Is that what you said? Or will it work? Okay, I can't hear well, so whatever you say, I'll say, oh, this is what you said, good. Okay, that's the right answer, okay? All right, so continue. 3x minus 6 is less than epsilon, and then what? 3 times x minus what? 2 less than epsilon. Well, that's what. There we have it. So what do? Divide both sides by 3. And now we have 0 is less than absolute value of x minus 2 less than epsilon over 3. So in other words, for whatever epsilon you choose, however small you want to make that epsilon, divide it by 3 and that'll be your delta in this problem, because that will guarantee it works. Okay? So, yeah, that was a lot like the other. They didn't give us a value for epsilon, they just left it in things. So, and that is a 3, by the way. I just noticed how ugly that is. You probably noticed it a long time ago. Let me make that look a little bit neater. Okay, not much, but a little bit. Okay, there's your delta. Let that be your delta. Whatever epsilon you choose, let epsilon be greater than 0. 0.00003, you know, divide that by 3, and then you got your delta. If you get the delta within that, guaranteed to give you epsilon. You're within epsilon on the y. All right, that was another fairly easy one. Now the ones that get to be a real pain in the neck or some other body part. Okay, so use the epsilon delta definition of a limit to prove that the limit as x approaches 2 of x squared. Anyone tell me what that is? What is that limit? 4. Okay, we know it's true. Now we have to prove it using the epsilon delta definition. Okay? So, we start by let epsilon be greater than 0. Okay, doesn't say a lot, but that's where you begin. So for each epsilon greater than 0, there is a delta greater than 0, such that you can use a straight line too. I like the 2 dots. Anytime your function value, x squared minus your limit, 4, is less than epsilon, whenever 0 is less than absolute value of x minus 2. And that's less than delta. Okay, it'll come back. Okay. Now, here we got a little bit of a problem. Okay? On first glance, it's sort of looking okay. It says to find an approximate delta. What would you do with this? What would be your first guess? Factor. That sounds like a winner to me. So that would be, what's the factorization of x squared minus 4? X plus 2 times x minus 2. Okay. Now, things are not looking too bad right off the top, because here you see this is already beginning to look like this. But rather than this being a number, like it was 2 or 3 before, it's now a variable expression. Okay? So we need to do something with that. Okay? Now, what we're looking for is a value for delta. Okay? So we wrote this now, and by the way, here's another thing that I don't know if you're aware of. If a product, okay, I left off a parenthesis there, or an absolute value bar, I don't know which that was, it's sort of in between the two. Here's something that I hope you know. This is the product that's this thing, okay? And this is always, and there's a thing called a triangle inequality. They say this is exactly equal to x plus 2 times the absolute value of x minus 2. Something in my gut tells me that should be less than or equal to it, but we'll start with it. So we're just going to say this is equal to that, and this is less than epsilon. Okay. Now, if we only knew what that was, or could define that, then we would have it not. Okay? Now, you're interested in finding values of x close to 2. That's what we're looking for, right? So you can choose x to be on some interval. And you get to choose. Something close to 2, let's just choose an interval between 1 and 3. Now that's not really all that close, but you're somewhere in there. 2 is in that interval. So let's choose something in between that. Okay? Now, to satisfy that restriction, let's let delta be less than 1. Okay? So if your delta is less than 1, then you're going to fit in there, okay? Because if you're within there, your delta 2 is 1 away from here and 1 away from there. So for a delta less than 1. Now that's not a very small delta, okay? But it is, some value, okay? So we'll do that. Now, for all the x's in the interval here, if your x, see this thing right here, x plus 2, if that's equal to 3, okay, a delta of 1, then this one right here, the x plus 2 okay, if you chose this x, the very top x you do, this would be equal to 5. If you chose the bottom x, that would be x plus 2 would equal 3. Pick the larger of those two, okay? That's going to be 5, okay? All right. Now, so what we're going to say is that this x minus 2, or x plus 2, has to be less than 5, right? It's got to be. I think we'll keep it in absolute values, because that's the biggest value can be if you're here. If your delta is less than 1, then this thing can't be any greater than 5, okay? Because this x of 3 would give you 5, and x of 1 would give you 3. So the maximum that could be was 5. So this thing right here has to be less than 5, okay? So if that's less than 5, then substitute that. 5 times absolute value x minus 2 is less than epsilon. Then divide this by 5. See, they didn't give you a number, so you pick a number. We have epsilon less than 1, and that puts the range here between 1 and 3. The maximum this could be would be 5 then. So choose that. That's the very outside, the very largest. So then divide by this epsilon by 5, and you will have this thing less than that. So this could be another delta. This is what we had as delta before, because that is now what this is saying. Okay? Now this seems like a really circular argument, and it really is somewhat circular. But what you wind up with is either delta is the lesser, it's either 1 or epsilon divided by 5. If you chose an epsilon of 15, then use this delta. If you chose an epsilon of 0.3, choose that delta, okay? And then either way, you choose the lesser of the two deltas, okay? And it seems sort of artificial and make-believe because you just sort of made up something here. But that gives you one delta. This gives you another delta. Pick the lesser of the two. If you're epsilon, yes. Okay. You just chose a delta. It said you want to be close to 2. Well, let's just pick a value, and a really easy value is 1. Let's get that your delta is going to be something less than 1. That means you could be, if x minus delta would be 1, x plus delta would be 3, if delta was less than 1. You just pick a value. You could have picked 0.73 if you wanted to do that one, but then it would be such weird math, okay? So pick something easy, 1, okay? Then proceed, and if that's the case, then you see this part is looking like what you need. This part you have to deal with. So if you use the x somewhere in here, then you can either choose the lesser or the greater. Pick the greatest. The most this could ever be would be 5 then, okay? So instead of putting x plus 2, let's put the greatest value it could be would be 5. Divide by that. Now here's another delta you have. It's either if you pick delta less than 1, that would be this. Okay, back that up a little bit. Or another delta would be this one or the other of these two. If your epsilon comes up being less than, like I said, if you chose an epsilon of 15, then you don't want to use this delta, you'll use this one, because 1 is less than 3. But if you chose a delta of an epsilon of 0.01, you'll use this one, okay? Because 0.1 divided by 5 is much less than 1. In fact, most of the time this will be the one you use. But you're just picking some value of epsilon to knock this one out so you can have this representing your delta. Pick something, anything. If you wanted it to be 0.03 here, then you have to get a really small epsilon to get less than that. But as soon as you do, if your epsilon is less than that, then you go with this. So whatever delta you choose here, that influences that one, and then pick the lesser of the two. If your epsilon is whatever you choose, any positive number, then you choose the delta that's the lesser of these two. Because once you choose the epsilon, you know this value. If that's less than 1, go with that one. If that's greater than 1, go with this one. So there's your delta. You found it either way. Okay? And all you're doing there is picking a delta, any delta you want to, that will get rid of this term. And choose the largest value here to get the value there. And then that makes a pretty small delta over there. And then you go with the lesser of the two. It seems really artificial, and it really is, okay? In reality, we just plug them in. That's usually what we're going to do when we're finding our limits. But this is the formal definition, and just like dressing up in a tux to me is no fun at all, this is not very much fun either, okay? So go. If y'all like dressing up with tuxes, you might love this definition. Okay, never mind. Homework exercises. As I said before, I'll go over this every time. Do any of the odds 5 through 9, okay? They're all at Calc Chat, number 5, because it has the little red number by it. That will be at Calc View. Now, if you do happen to get the book, which is not a bad idea to do, you can get your cell phone and just pick on this, and you'll go straight to that problem right there. So you don't have to go to a website. You can go right there on your cell phone. The QR code takes you right there. So do any of the odds 5 through 9. They're all at Calc Chat. Number 5 is at Calc View. Do any of the odds 11 through 17. They're all at Calc Chat. None of those are at Calc View. Do number 19. It's at Calc Chat. Then do either or any of the odds 21 through 27. They're all at Calc Chat. 23 is at Calc View. Do 29. It's at Calc Chat and Calc View. Do 31. It's at Calc Chat and Calc View. Do 33. It's at Calc Chat. Do either 35 or 37 or both. It's up to you. They're both at Calc Chat. Do any of the odds 39 to 43. They're all at Calc Chat. 41's at Calc View. Do any of the odds 45 to 55. They're all at Calc Chat. 47's at Calc View. Do 57. It's at Calc Chat. Do 59. It's at Calc Chat. You can do 61. It's at Calc Chat. Now, some of these have this little symbol by it that indicates an exercise or a part of the exercise where you are to use graphing technology, like a graphing calculator or a computer system or something like that. You might be able to do it without it, but you might find it easier with it. Then you can explore doing either 63 or 65. That'll be up to you. Try doing 67. That's sort of an applied problem. And by the way, all those are at Calc Chat. Try doing 69. It's at Calc Chat. Well, let's see. or 671, it's a CalChat. They throw in a couple of true-false most of the time. I really don't care for true-false. I'm not going to ask you true-false on the test. However, thinking through it and seeing why it's true or false, there is some value to that, conceptually. Don't expect to see something like this on the test, but do either 73 or 75. They should both be at CalChat. Do 77, it should be at CalChat. And then 79 should be at CalChat. Now, for those of you who are math majors or some other major who is going to be doing lots of proof, then you may want to go on and pursue 81 and or 83, because they are both proofs. They should be at CalChat. So if you're interested in that. Now, these Putnam challenges, only if you're really a glutton for punishment. I mean, that you really want to dig a little deeper, okay? These are pretty tough, so don't expect anything like that on the test, okay? These are something about the Putnam Prize competition, whatever that is, it must be pretty tough. All right, any questions on 1.2? If not, we'll move on to 1.3. Thank you, thank you, thank you. These, to me, are much more fun to do than the definition. I don't want to bias you with my bias, but I really prefer analytic to graphing, numerical, or formal definitions, as you may have told. Okay, we're still in Chapter 1, Limits and Their Properties. 1.3, Evaluating Limits Analytically. All right, let's go for it. We'll evaluate limit using properties of limits, so we've got to learn what they are first. We'll develop and use a strategy for finding limits. We'll evaluate a limit using the dividing out technique, which I've already showed you. We'll use evaluating a limit using the rationalizing technique, which is multiplying by conjugate. And then we'll evaluate a limit using the squeeze theorem, which is kind of fun, but it gets a little esoteric as well. So not one of my favorites, but it's certainly useful at times. So let's first start with the properties of limits. The limit of f of x as x approaches c does not depend on the value of f at x equals c. Remember, our definition said c has to be within some interval, and the function has to be defined within that interval at all values except possibly at c. It may not even have a definition at c. It's okay. You're just doing as x approaches c. It may happen, however, that the limit is precisely f of c. If it is, plugging in works really nicely. In such cases, we evaluate the limit by direct substitution, plugging it in. So that's always the first thing I try. If I'm trying to determine the limit of f of x as x approaches c, first thing I'm going to do is plug in a c. See what we get. See what we get. Okay? And here's the possibilities. We're either going to get an answer, an exact answer. Then we know what the limit is. Or we will get something that's impossible, like 17 over 0. Okay? If you get that, there is no limit, guaranteed. Or we get something like 0 over 0, which is indeterminate, and then you have to do more investigation. So the first thing we're going to do is plug it in. Such well-behaved functions are continuous at c. If the limit as x approaches c of f of x is f of c, then that's the easiest case. If they're continuous at c, then we're fine. Remember, we said they're continuous everywhere in the interval except possibly at c. If they are continuous at c, piece of cake, okay? And I like cake. Okay, so here's the theory. Basic limits. Now, these are ones that are not going these are almost duh type problems, okay? The limit is x approaches c of b. Well, b is a constant function, right? So if x is approaching c, whatever c is, guess what? it's still going to be b. Because if it's a constant function at all values of x, then the limit as x approaches c of a constant is that constant. It doesn't matter what x is approaching. If it's a constant, it's always going to be that constant. That's one of the dull ones. Okay. Now, this one's also pretty dull. The limit as x approaches c of x, okay, I meant to open the door for you, sorry. Okay, would be c. If x is approaching c, the limit of x is c. Pretty obvious, right? So that one's a really easy one. Now, this one is also pretty obvious. The limit as x approaches c of x to the nth power is going to be, plug it in, c to the nth power. Okay? So actually plugging in x equals c will be c. You know, x to the n, plug it in, x equals c, that'd be c to the n. And this one, there is no x in this one, so the limit of b is b. Okay, that's pretty obvious. So get these three down. These are just givens. They almost are too simple to even want to write down, but get them. They're there. Okay. So, okay. I don't know what to do with this. To me, they should have left that blank. So what is the limit as x approaches 2 of 3? 3, okay? 3 is 3 is 3 is 3, no matter what x is. So that's 3. Don't even know why they wasted the ink to write the answer down. Okay, how about this one? The limit of, as x approaches -4, the limit of x as x approaches -4 is -4. You got it. Y'all are good. Okay. The limit as x approaches 2 of x squared is 4. Y'all already done one like that, 2 squared, which, by the way, is, for those who are a little rusty on your powers, is 4. Good. All right. Those are those. Don't you rush, your whole test would be like that and dream on. Slap yourself, wake up, you're dreaming. Okay. So here's some of the other properties based on those first three. Let B and C be any real numbers in the world. N has to be a positive integer, not negative integer, not fraction, not decimal, positive integer. Okay? That excludes 0, by the way. 0 is not positive. It is an integer, but not positive. B and C are any real numbers. Let F and G be functions with these limits. The limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is equal to capital K. We just happen to know those are those limits. Okay. Now here are some of the properties of a limit. Scalar multiple. If you have the limit, you know what limit of f of x is, that's L. If you have a function that's just a constant multiplied by f of x, what you can do is pull the constant outside the limit, and then you have b times the limit as x approaches c of f of x, which you know to be L, so that would be b times L. Okay? So a constant can always be pulled out of a function and then evaluate the function and multiply it by the constant. Sum or difference. The limit of x approaches c of f of x plus or minus g of x. The limit of a sum or difference is the sum or the difference of the limits. Okay? That hopefully sort of makes sense as well. Well, if the limit of this is L, the limit of that one is K, then the limit of the sum is L plus K, the limit of the difference is L minus K. Okay? Product. The limit of a product. The limit is x approaches c, f of x times g of x is the limit of f of x, which is L, times g of x, limit of g of x, which is K, so that would be L times K. Pretty straightforward. Quotient, the limit is x approaches c of f of x divided by g of x is the limit of f of x, which is L, divided by the limit of g of x, which is K, except now you have to make sure K is never equal to 0. So whatever value if when x approaches c, if this g of x was 0, then this limit doesn't exist. Okay, pretty obvious. Okay, and then sort of similar to the third one we did before of power, the limit is that x approaches c of a function raised to the nth power would then be the same as its limit raised to the nth power. Okay. So, scalar multiples, you just multiply the limit by the scalar. Sum or difference? Sum or difference of the limit of a sum or difference of two functions is the sum or difference of their limits. The limit of a product of two functions is the product of their limits. The limit of a quotient of two functions is the quotient of their limits as long as the denominator is not 0. And the limit of a power of a function raised to a power is the limit raised to the power. If that limit exists, it's it. So, pretty straightforward and hopefully sort of, oh yeah, that makes sense. Rules, properties. So let's do this. Find the limit of this. Guess what my suggestion would be? Delete it. Plug it in. What would that be then? Did someone say what? 19? Perfect. That was 4 times 2 squared. 2 squared would be 4. 4 times 4 is 16 plus 3 is 19. Now, if you wanted to drag it out to ad nauseum, you could say this is the limit of 4x squared as x approaches 2 plus the limit of 3 as x approaches 2. Yeah, we know what that is, okay? Then you can say this is 4 times the limit of x squared, and then that would be the limit of 2 squared. Yeah, so you could drag it out in many, many steps, and I'm sure the book's going to do that. So let's see what they do. Yes, they split it into the sum of 2 limits, which is fine. And then they bring out the constant multiple, which is fine. And then they plug in, finally here, you could have plugged it in up there just as well, and you get 4 times 2 squared plus 3, which is 19. So why do all that intermediate steps? But if you need to do it, do it. It's perfectly legitimate. But if you can see, just plugging in there is so much easier. Okay? Quicker. All right. That limit is reinforced by the graph. And by the way, that is a polynomial. It's a quadratic with a 4, which was a vertical stretch. 3 is a horizontal, is a vertical displacement or shift upward by 3. And then 4x squared, so it's going to be 3 is going to be your 0 here, and you've stretched it by a factor of 4. So yeah, that's what it looks like. And when x equals 2, you're at the value 19. Yeah, I draw the graph every time just to check, right? And yeah, right. Okay. So let's look at some more of these properties. The limit, any questions on that? I sort of went through that pretty quickly, but y'all seem to know it. The limit, as x approaches 2 of the polynomial function, that one that we just did, is simply the value of the polynomial when x equals 2. It's exactly what we did. This direct substitution property is valid for all polynomial and rational functions. Polynomial functions, all of them, rational functions, as long as you don't have 0 in the denominator, which is what we've run into before. Now, if you have a 0 in the denominator, you have to then ask what's the value in the numerator. If that value in the numerator is also 0, you have an indeterminate form. Proceed and see if you can figure out. If that numerator value was not 0, hang it up, Jack, undefined. Limit does not exist, always. Okay, so here's theorem 1.3, limits of polynomial and rational functions. If P is a polynomial function, and C is a real number, then the limit of, as x approaches C, of P of x is, guess what? P of C. Just plug it in, plug it in. If R is a rational function given by R of x is equal to P of x divided by Q of x, in other words, the ratio of two polynomial functions, and C is a real number, such that the Q of C is not 0, then the limit of the rational function R of X is this will be R of C, which is simply P of C divided by Q of C. If this Q of C is 0 and P of C is not 0, the limit does not exist. If the Q of C is not 0, that's what your answer is. If the Q of C is 0 and P of C is 0, then you have some more investigation to do to see if that's an indeterminate form, to see if you can decide on this value. Okay, makes sense? All right. It seems like to me, yep, no, we were right. Here's example 3, by the way, for those with books, page 64. Okay? Find the limit as x approaches 1 of this one. Anyone want to make a guess? Okay, what's your final answer?
I just plugged in 1. I got
Okay.
1/2.
And you got what?
1/2.
Okay, let's try it again. Say again? 2. Because the numerator becomes 4, the denominator becomes 2. 4 divided by 2 is 2. Okay? Make sense? Plug it in correctly. Okay, all right. I'm sure they'll string it out a little bit more than that, because the denominator is not 0 when x equals 1. You can apply the theorem, and then you just plug it in, and you have 1 squared plus 1 plus 2. That'll be 1 plus 1 is 2 plus 2 is 4, over 1 plus 1 is 2, and that's 4 over 2, which is 2. And here is a graph of half of that function. This isn't the whole graph. The whole graph is also going to be, it has a vertical asymptote at x equals -1. That's why this is going up pretty steeply there. And it has a slant asymptote through here. And you know that because that degree is 1 more than the degree of the denominator, so you can do a division. In this case, you could do synthetic division, or you could do regular polynomial division, and you'll find out there's the line, whatever it turns out to be. Okay. So the other half of this function will be down here. Do it like this. Somewhere down there. But you only need that one because you're only interested where x equals 1. Make sense? All right. Polynomial functions and rational functions, 2 of the 3 basic types of algebraic functions. The next theorem deals with the 3rd type of algebraic function, one that involves a radical. Okay? So here's the theorem that deals with that. Okay? Let n be a positive integer. Positive integer. The limit below is valid for all c's when n is odd, and is valid for c greater than 0 when n is even. Okay, and that's because square roots of, or no, not quite right, even roots of, you can only take the even root of a positive number. You can take the odd root of any number, positive or negative. So if n is positive, this is true for all. If n is negative, if n is odd, this is true for all n, all x's. If n is even, then x has to be greater than 0. C has to be greater than 0. So the limit of the nth root of x is the nth root of c, if this is defined. Okay? If n is an even number, then c has to be positive. You can't take the even root of a negative number. But if n is odd, that's good for any value. And the proof of that theorem is given in Appendix A. I can't wait to get back there and read it. Okay. Knock yourself out. Okay. The next theorem, let me make sure they're not skipping anything. Yes, they are, aren't they? No, they're not. Okay. want to make sure I wasn't going too fast here. Say sometimes we'll skip examples. I like to go back now. Next theorem greatly expands your ability to evaluate limits because it shows how to analyze the limit of a composite function. Okay? So if f and g are both functions such that the limit as x approaches c of g of x is some value L, and the limit as x approaches L of f of x is f of L, blah, what a surprise, then the limit as x approaches c of f of g of x would be the limit, it would be, okay, now here's what they're doing. You're taking the function, the limit of a function of another function, composite function here, take the outermost function outside and take the limit of the innermost function, evaluate that limit, and then take the f of whatever that value is, the limit of this one is, and that gives you that. Okay. Now, this is far more complicated looking than what it is. When you actually do it, you just plug in the x, just like you always do, and do your evaluation. This makes it seem like it's something new and unusual, and it really isn't. It's just doing the same thing we've done before. So let's do a couple of these, okay? Let's do the first one there. What's the limit as x approaches 0 of the square root of x squared plus 4? Say again? 2. Perfect. Oh, I'm sorry. Shouldn't hit the desk hard. It makes it go out. It's 2. You just plug in 0 here, and 0 plus 4 is 4. Square root of 4 is 2. Okay, how about this one? The limit as x approaches 3 of the cube root of 2x cubed minus 10. Okay, take as many steps as you need. What you get? Okay, lead me through it. That would be the cube root of 2 times 3 squared minus 10, which is the cube root of 2 times 9, which is 18 minus 10, which is the cube root of 18 minus 10, which is the cube root of 8, which is 2. Perfect. Same answer. Hi, okay. Did I stop and say, wait, now this is a composite function, I have to do... No, you don't need to do that. All you do is plug it in and do the math, okay? Just that simple, basically. Okay? So I said that last theorem made it sound a lot more complicated. It really isn't. Okay? So let's see how they do it, in case they do it a slightly different way. Any questions before I erase it?
So when we get a test, do we have to use these functions?
All right. Now there is an excellent question, and I'm glad you asked it because I meant to say this when I was doing the syllabus. Okay. The class, for some odd reason, decided they preferred take-home tests. Mystery to me. Okay. Now, because it is a take-home test, really glad you asked, and this isn't why you asked, but I'm glad you did. What you have to do when you're taking these tests is show your steps. Now, your question, do you have to show every step? Just what I did was showing. Plug it in, doing, that's fine. You don't have to say which theorem you're using, all this kind of stuff. You just have to show your steps. Before I would have said, all I'm interested in is the answer. But I have received a little bit of flack from some of the other instructors for giving take-home tests, okay? And so, therefore, to ameliorate some of their concerns, I want you to show all your steps, okay? So if any of you are ever back again, it's always going to be the case. For take-home tests, you need to show all the steps. If all I've got is an answer, even if it's a correct answer, you only get half the credit. Okay, so if that's all you do is give me correct answers, you just get a 50 on the test. Okay, sorry about that. You have to show your work. Okay, Now, do you have to show every gory detail? No. Basically, what I do when I'm solving them here, that's the degree of close to it. If I can follow your logic in your steps, I give you full credit. But if you jump from something to something with not any obvious way of how you got there, no, you're going to lose some points on that. Okay. Is that sort of what you were asking from the other way? Okay. All right, let's see how they do it. Okay. You certainly don't need to go into this much detail, okay? You can just plug it into the original thing and show that that's what you get. That's what you got, okay? I know you did it probably in your head, and if it's that obvious to you, it'll be that obvious to me. But guess what? I don't think you'll have a single test question that's quite that simple. So show enough work to let me know that you knew what you were doing, okay? And also, but that's way more detail than I'm even looking for. Of course, if you write that much down, you get full credit too, okay? You can conclude that. So not all you have to do is plug in a 0 for x and show it. It's done. Okay, this next one, again, way stretched out, way beyond what you need to do. Just show me, just like we did, that you understand how to plug it in, take the cube root, and you get it. Okay. And even they will quit doing this after a while. They'll just plug it in and go. All right. So that was example 4. All right. Now, we talked about 3 types of algebraic functions: polynomial functions, rational functions, and radical functions. Now let's go to other non-algebraic functions. You'll see that the limits of many algebraic functions can be evaluated by direct substitution. The 6 basic trigonometric functions also exhibit that desirable quality as shown here. Okay? If c is any real number in the domain of a given trigonometric function, then the limit of x approaches c of sine x is sine c. The limit of x approaches c of cosine x is cosine c. The limit, and by the way, these are good for what domain? Sine and cosine. Any limitations on the domain? All real numbers. Now, let me say this. Unless something is designated otherwise, always assume we're dealing with radians. Don't ever assume we're dealing with degrees unless you see a degree sign. Like if you saw x approaches 60 degrees, then that's going to be degrees. But if you saw x approaching 60, assume radians. Okay. Whichever you're doing, all real numbers are in the domain. The limit as x approaches c of tangent x is tangent c. Here we have to stop and pause a minute. What can c not be there? Any ideas? What can you not take tangent off? Anyone know? Remember? You better, okay. Half pies. All your half pies, tangent is not defined. Vertical asymptotes every half pi. Minus half pi, minus 3 halves pi, minus 5 half pi, 3 half, yeah. All the half pies, tangent is not defined. Because tangent is opposite over adjacent at the half pies, at pi halves, 3 half pi, all these, your adjacent is 0. You can't have that. Okay, cotangent. Any limits there? The limit is x approaches c of cotangent x is cotangent c, as long as c is not what? A whole pi. Pi, 2 pi, 3 pi, 0. You know, can't do those, okay? Secant, the limit is x approaches c of secant x is secant c as long as c is not some of you are in serious trouble because you're in my trick class, okay? The rest of you, I can let you skate a little bit. This is just like tangent, the half pies. And the limit is x approaches c of cosine x is cosine c as long as c is not a whole pi. Hey, y'all got it. Okay, good deal. All other values is. So wherever it says, let c be a real number in the domain of the trigonometric function, the domain of tangent and secant do not include the half pies, and the domain of cotangent and cosecant do not include the whole pies. Okay. So let's give this one. The limit, oh man, why did I do this? What is that? You shouldn't have been looking. What is it? 0, because tangent of 0 is 0. Okay? How about that? What's that? I can't hear. I hear something, but I mind the way. Is that what you're saying?
Negative pi.
Negative pi, perfect. Because x would be pi, and cosine of pi is -1, so that would be a negative pi. Perfect. Everybody see that? Understand why? Okay, good. All right, how about that? Say again? 0, because the sine of 0 is 0, sine squared. 0 squared is still 0. Yeah, perfect. Oh, that's it. So those are example 6. I don't know why they give you the answers. You ought to just do it. So, what's the strategy for finding limits? Sound pretty simple to me. Plug it in, plug it in. Okay, that's a pretty good strategy, isn't it? Well, let's see. There's something else to be done here. You studied several types of functions whose limits can be evaluated by direct substitution. That knowledge, together with the next theorem, can be used to develop a strategy for finding limits. So functions that agree at all but one point. Let C be a real number, any old real number, f of x equals g of x for all x's not equal to c. Okay? So f of x is equal to g of x for all x's not equal to c on an open interval containing c. The limit of g of x as x approaches c, if that limit exists, then the limit of f of x also exists, and that would be the same. Okay? What in the world are they saying here? Well, it's saying these two functions are the same, except at x equals c, they're not the same. Well, if they're the same everywhere else on the open interval containing c, then the limit, if the limit of g of x as x approaches c exists, then the limit of alpha of x is going to be the same because it's the same everywhere except at c, but as it's approaching, it'll have the same limit. So that's sort of a... Okay, well, by the concept, where is the real... do you run in the real functions? That would be the case. Maybe here, okay? And this is just like... In fact, this is one we did before. Remember what the limit was? Second? Yeah, turn back. It was one of the first ones we did.
Or like that
Indeterminate. Okay, whatever I said. Okay, indeterminate form. But, remember what we can do with that? Factor the numerator, and that is x minus 1 times x squared plus x plus 1 over x minus 1. Divide those out, and then take the limit as x approaches 1. And what would that get? Say again? 3. Okay, I thought you said 2. Okay, 3. Perfect. Okay, that limit is 3. Okay, now how does that relate to that previous thing there? F of x and g of x are the same everywhere except x equals c. Well, basically, what we're saying is this is the same as that except that x equals 1. Okay? This and that are the same except that x equals 1. X equals 1, this one's not defined, that one is. Okay? So if they are the same everywhere except that, then the limits are the same, even at the place where that is. Which is basically saying your indeterminate forms. Just if you can eliminate the thing that makes it confusing, yeah, then you can find the limit. Okay? And let f of x equal that, which of course it is. By factoring and dividing out common factors, you can see that's the same as that. So the f of x is the original one. The g of x is the one with it factored out. They're the same everywhere except that x equals 1. F of x is not defined, g of x is. So the value of the limit of f of x will be whatever the limit of g of x is, which is 3. Okay. Yeah. And remember, we plugged in points here and had the point here and here and here, and and we sort of drew it in, but left the hole there. But g of x doesn't have a hole in it, because g of x doesn't have a denominator. But because they're the same everywhere except there, the limits will be the same at both. Since the limit of g of x is that, that'll be the limit of f of x. Just like we did before. Okay. Because the limit of g of x approaching 1 does exist, you can apply theorem 1.7 to include the limit of f of x, g of x have the same limit, x equal 1, which is 3. So basically that leads you to this property of simplify your rational expressions if you can and eliminate your problem point, x minus 1, then you wind up with the limit. Okay? And that would be 3, which is what we did earlier. I shouldn't have. I should have waited till now, but I just couldn't resist. All right. Now, y'all have to sort of help me keep up with time, because I'll get carried away. I can just go and talk about this stuff forever. So don't let me go extra. Now, I'm really serious now. In my class yesterday, I actually went way over one time. I didn't care. The students didn't care. I didn't care. This one, I care. You know why? I've got 5 minutes before my next class, so don't let me run over. Okay. So here's the strategy for finding limits. Learn to recognize which limits can be evaluated by direct substitution. Okay? Now, you can always try. You don't have to memorize and say, oh, are these fit this theorem? No. Try. And if you get something that won't work, will never work, the limit doesn't exist. But if you get something that's indeterminate, then you have to do something else. If you get something that just gives you the answer and there's no ambiguity, then you got that. All right. Now, when the limit of f of x as x approaches c cannot be evaluated by direct substitution, try to find the function g that agrees with f. This is a weird way of saying it. For all x's other than c. In other words, do some manipulation of f, eliminating common factors, multiplying by conjugates, whatever it takes to simplify it. If you can get some function that does have a limit that's going to be the same everywhere except at the problem point, then you've got it. Okay? Then apply theorem 1.7 to conclude analytically. If you can get something that eliminates the problem here and is the same here as everywhere except at that problem point, then that's going to be the limit. And you can use a graph or a table to reinforce your conclusion. Frankly, analytic, to me, reinforces better than a graph or but the others can be helpful, especially if you got a graphing calculator. Okay. A lot of blah, 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 but basically plug it in. If when you plug it in, you get an answer and it's unambiguous, that's your limit. If when you plug it in, you get something that can never happen, 7 divided by 0, not going to exist, not going to happen, limit does not exist. But if you get a value that's 0 over 0, indeterminate, then try some technique to see if you can come up with an equivalent expression. Okay? So, the first we're going to look at of those, and make sure we're not skipping anything here, is the dividing out technique, which we've just done, and we had done it earlier. One procedure for finding a limit analytically, dividing out technique. That technique involves dividing, diving out common factors, okay? Ooh, is that way? No. Does it say that in the book? That would be really funny. I don't guess it says that directly. It means dividing out common factors. Evidently, the graphics guy messed up. Okay. So, can we find a limit here? What would you try first? Plug it in. Let's see what we get. Oh, wait, let's not even bother, can we? Your denominator is going to be 0. No, we still bother. Plug it in up here too. What do you get? Is x approaching negative 3? What's x squared? Second? 9 minus 3 minus 6 is 0. So you do have an indeterminate form, so yes, we'll proceed. Just because you have a 0 here, always then check there. If you get 0 over 0, proceed. If you get 17 over 0, don't proceed. Don't even mess with it. It's not going to happen, okay? But if you get 0 over 0, see if you can do anything else. And what might you be able to do here? What might you do to that numerator? Factor it, okay? Now, I know you remember all your factoring techniques, right? How would that go? Oh, that's not a 2, it's a 3, okay? It'll come back in a minute. There we go. Okay, the only possible factorization for x squared is x times x, right? That was we're unfoiling, okay? X minus 2, x plus 3. I think that works, and then you can divide out the x plus 3's, and what's the limit as x approaches minus 3 of x minus 2? Negative 5. There's the limit, okay, without ambiguity, okay? Certainly, the first function isn't, you can't have x equal minus 3 in it, okay? But the limit as x approaches minus 3 does exist at negative 5. All right. Let me clear my chicken scratch. Any questions before I clear it? Okay. Wow, they took all that much time to say what we already said. Direct substitution fails, but it gives you a 0 over 0, which is indeterminate, so continue. Because the limit of the numerator is also 0, the numerator and the denominator have a common factor, and then, okay, I'm not sure I agree with it. Because the limit of the numerator is also 0, the numerator and the denominator have a common factor of x plus 3. That's not always the case, but anyway, in this case it's true. Factor out that, and then divide it out, and you get the g of x, and that is evaluatable at x equal minus 3, and you get negative 5. Whew. Took them a long time to get there, but they got there. Make sense? Okay. Oh, and by all means, draw your graph. I mean, those are so much fun to draw. The x minus 2 is going to be a line that goes through y is equal to minus 2. with a slope of 1, and down there at -3, it would have been a -5, except in the original function it couldn't be at -3, but you got a hole in the graph at -5. Good deal. Any questions? All right. Finally, they get around to saying, in example 7, direct substitution produces a meaningless fractional form of 0 over 0. That's not meaningless. There's some meaning there, but it's indeterminate, but that means you can proceed further. If it had come out -13 over 0, hang it up, the limit won't exist, okay? But this time, you don't know whether it has a limit, but see if you can use one of these techniques. When you try to evaluate the limit and encounter that form, remember that you must rewrite the fraction so that the new denominator does not have 0 as its limit. One way to do this is dividing out common factors, which we just talked about. So why didn't they talk about this first? I don't know. Let's see. The second technique is rationalizing technique, which is the same as multiplying by a conjugate. Okay? They call it rationalizing technique, which involves rationalizing either the numerator or the denominator of a fractional expression. Okay? We know that rationalizing the numerator or denominator means multiplying the numerator and the denominator by the conjugate of whichever one you're trying to rationalize. Okay? So in this case, depending on what you're doing, as x is approaching 0, well, wait. They're not taking the limit of this. If they were taking the limit as x approaches 0, what would you say the answer was? If there was a limit as x approaches 0 here, what would you say? Second? Not indeterminate. Does not exist, because as x approaches 0, this would be 0 plus 4, which is 4 over 0. That's not indeterminate at all. That does not exist. So this would not be a good one if you're taking a limit as x approaches 0. Or it would, it just has no limit at all. It does not exist. But all they're showing you here is how you rationalize. Okay? Now, you're not worried about the denominator here, you're worried about the numerator. Okay? Because that has a radical form. So how would you rationalize that expression? What would you multiply by? Anybody? Anyone? The square root of x, you say minus 4? Perfect. But if you do it in the numerator, you got to do the denominator as well. Okay? Now, I'm not going to say this is going to get you anywhere productive, but let's just see what it gives you. What's your numerator give you? Anybody? X minus 16 over x times the square root of x minus 4. Okay? Okay. That doesn't give you anything that can be eliminated, but that's how you would rationalize it, the numerator. Okay? So, let's actually do one. Okay. Is this worth doing? What would you do first? Plug it in. What does it give you? You get what? 0 over 0. That's indeterminate. It's worth proceeding. Okay? If you got an answer, you're done. But if you got 0 over 0, keep going. So what would you do? I think we already did this one, but let's do it again. Okay, multiply by the conjugate. What would be the conjugate of that? Plus 1. You got it. But if you multiply the numerator, you got to multiply the same thing by the denominator. X square root of x plus 1 plus 1. Because that is itself 1. You can multiply by 1 anytime you want to. Okay, so what does this give you? I'm going to write down the limit as x approaches 0 of, what's your numerator now? X plus 1 minus 1 over, now don't multiply through that, let's just write it down, x times the square root of x plus 1 plus 1. And what happens in the numerator? Those two add to 0. You're left with just an x. The x's can factor out, so this will be the limit as x approaches 0 of 1 over the square root, oops, got a little carried away there, square root of x plus 1 plus 1. Now what can you do? Plug it in again, and what do you get? 1 over 2. Perfect, perfect, perfect. Make sense? Everybody see how it works? Any questions? Okay. Let's erase this and see how they did it. Anyone need it up there a little longer? Okay. By direct substitution, you obtain the indeterminate form. So always substitute first. If you get an indeterminate form, then proceed with something else. If you get something that can't ever happen, in other words, undefined, there is no limit. Just hang that up and say no limit. If you get an answer, that's your answer. Okay, but you get indeterminate form. So now we proceed to, oh, they're just showing it's an indeterminate form. We had already done that. Very good for them. So now proceed by rationalizing, in this case, the numerator by multiplying by the conjugate of the numerator. But if you multiply the conjugate of the numerator by this, you have to multiply the denominator by the conjugate of the numerator as well. And when you do that, you get x plus 1 minus 1 over x times the square root of x plus 1 plus 1. Okay? That would be x over x times the square root of x plus 1 plus 1, which will then be x's divide away. You're left with 1 over the square root of x plus 1 plus 1. Now you got to remember, x still can't be 0 in this because you came from that where x can't be 0, but you can still plug it in. And when you take the limit of that value there, I've got something in my eye, plug in a 0, you get 1 over 1 plus 1, which is 1 over 2. And there is your limit. All right, good deal. Any questions? Same thing we got. And then they draw the graph. Oh, what a joy. Okay? Now, this is not quite the same as the one we did before. It was going up, if I remember right. But notice here, this is still not defined for any x's less than minus 1. So there are no values here. At minus 1, it is negative 1 over negative 1, which is 1. And then, because of the manipulation here, it's going down like this. Crosses at minus 1/2. It just keeps going down. Okay? Good old square root function, but it's got been reflected across an axis. All sorts of things have happened to it. Okay. All right, any questions? Oh, and let's just show the table so we can figure out all these things for very complicated fractions. Pull out your calculators, plug in, and you're doing this to the original function, okay? If you plug in this value, you get that one. This value, closer to 0, but not super close, you get that one. Plug in there, you get that one. So this one, you get there, you're getting closer and closer to 0.5. Coming from this way, something less than 1/2, closer to 1/2, closer and closer to 1/2, really close to 1/2. So yeah, that's going to 0.5 as well. So if you like to do these, do them by all means. But to me, we've already shown it analytically. Why mess with it numerically? Okay. Now, the next is the squeeze theorem. Okay. I've also heard this called the sandwich theorem. I like sandwiches better than squeezes. So anyway, the next theorem concerns the limit of a function that is squeezed between two other functions, each of which has the same limit at a given x value. Okay? So basically what you've got here is a function g that's always greater than or equal to the function f. That's what you got. And that's always greater than or equal to the function h. Okay? Now, f is a very difficult thing to determine, and in fact, it doesn't have a value at x equals c. But, because g is always greater than or equal to f, and f is always greater than or equal to h, they have it the other way, that h is less than, doesn't really matter. But because of that, at every value, but at this value right here, the value where f is not defined, it happens to be that both g and h are defined, and they have the same value. If indeed that's the case, f has to have that value too, even though it's not defined there. Now, it would seem, just on looking at this, you have to have a lot of conditions met here, that h is always less than or equal to f and always less than or equal to g. Now, this is in some thing. It could be out here things get crossed up, like here, this way set down below h, but that's all right, as long as in some interval around c, this is always true, okay? But then, it has to be that g and h have the same value at the place where f doesn't have a value. And if that is the case, then that's the limit for f. So it seems like an awful lot of really specific conditions have to be met before you can use it. But sometimes it's pretty surprising how it will work, and all those conditions can be met. All right, so here, that was it graphically. Here it is a bit more formally. If h of x is always less than or equal to f of x, and f of x is always less than or equal to g of x, for all x's on some open interval containing c. It doesn't have to be a huge interval, just any open interval containing c. It could be really close to c, except possibly at c itself. It may not be the case. That's going to be true here at c. And if the limit of h of x is x approaching c is L, and it happens to be that the limit of g of x is x approaching c is also L, then it has to be the one that's in between the two, squeezed in between the two. The limit of this does exist and is equal to L. Okay?
11.25.
That's what? Oh, it's time. How sad. Okay, we will pick up then. I'm glad you caught that. We'll pick up with 1.9 next time. It's going to be the same slide as this one, so we'll come back to here. Let me give you a few homework exercises. We almost finished 1.3. You can do any of the odds, 5 through 21. They're all at Calc Chat. 7's at Calc View. Do any of the odds, either 23 or 25. They're both at Calc Chat. 25's at Calc View. Do any of the odds 27 through 35. They're all at Calc Chat. 29's at Calc View. Do any of the do either 37 or 39. They're both at Calc Chat. 39's at Calc View. Do any of the odds 41 to 45. They're both at Calc Chat. All at Calc Chat. 43's at Calc View. Do any of the odds 47 to 55. Through 61. They're all at Calc Chat. 53's at Calc View. Do any of the odds 63 to 73. They're all at Calc Chat. 65's at Calc View. Do any of the odds 75 to 81, they're all at Calc Chat. 75's at Calc View. and do any of the odds 83 to 89. They're all at Calc Chat. 83 is at Calc View. And we'll hold off on the others until next time. All right, good deal. Good deal. We'll see you. Have a good weekend. We'll see you on May. 2 days of class next week. Can you believe it? What a joy. Okay. Take care. Have a good weekend.